This is notes on the gas laws. There's four of them, and how they can actually be combined into something we call the combined gas law. So after this video, there is a little video you can watch, a TED Ed video, where they kind of show you with little kind of illustrations some of the different gas laws. So we'll start with Boyle's gas law. So Boyle's law is dealing with pressure and volume, and they are inversely related to each other. So as pressure goes up, volume goes down. And when we graph it, if we put volume on the x and pressure on the y, you'll see this inverse relationship. Our lungs, as we increase the volume in our lungs, that causes the pressure to decrease, and vice versa. Some of the next laws are going to deal with temperature. So Boyle's law, pressure and volume, we were holding temperature constant. So before we talk about temperature in the next gas laws, we need to know that we always have to use Kelvin temperature when we do calculations with the gas laws. And this is because 0 Kelvin is absolute zero. There's nothing lower. There's no negative values. Otherwise, if we had negative temperatures, then we would get answers that wouldn't make sense, like negative volumes and things like that. So absolute zero is a temperature that we on Earth have been able to get within thousandths of a degree of it, but not there all the way, because there's always some input of heat energy somewhere. So at absolute zero, all motion particles would stop. Also in outer space, if far between any planets, the temperature is really close to being 0 Kelvin. So to convert temperatures to Kelvin, it's just a simple taking your Celsius temperature and adding 273. So you will be doing that a lot in the numerical parts of these gas laws when you start to calculate. Another thing that you're going to see from time to time is something called STP. And STP stands for standard temperature and pressure. So the standard temperature, so if I said, hey, I have a gas at STP, then I would know that we are at 0 degrees Celsius, which is really chilly. That's 32 Fahrenheit. And we would again have to convert that into Kelvin. So it would be 273 Kelvin. The pressure is any one of those pressures equal to 1 atm, 760 millimeters of mercury, 101.3 kilopascals. Those are the pressures that would be what this STP are showing. So you would just pick the one that works for you in terms of the unit that it's in. There's also something called SRC. This one's a little bit more reasonable room temperature. So this is standard room conditions. The pressures are the same as STP, but the temperature now is like a nice 25 degrees Celsius, which is about, I don't know, 75 or 70-ish Fahrenheit. So sometimes we'll have a question in a calculation where we're talking about, I may say I have a gas at SRC. Then you would assume I'm talking about 273 Kelvin and for 1 atm for the pressure. So has this ever happened to you guys in the winter? Bring your balloon outside and it will deflate, and then it will reinflate itself when we get into our warm house or car. And this is an illustration of Charles' law. So Charles' law is talking about the variables of volume and temperature, and we're holding pressure and the amount of the gas constant. So volume and temperature are directly proportional now, so not inverse like the Boyle's law, but directly. So as temperature goes up, volume goes up. So when we graph it, our graph is going to look different than it did for the Boyle's law, and we'll get this this would be what we would see with a direct relationship or directly proportional. We also have Gay-Lussac's law. In this law, we're talking about pressure and temperature. We're holding the volume constant and also the amount of gas or the moles of gas constant. So this is the equation for the mathematical part of it, and pressure and temperature are directly proportional to each other. So if temperature increases and the volume can't increase because we're holding that constant, then there's going to be more collisions and more pressure. So again, whenever it's a direct relationship, you're going to have this kind of a graph. So as temperature increases, pressure increases. They both increase together, or they would both decrease together. One last law before we get into combining all four of these is Avogadro's law. And Avogadro is the first time now you're seeing the mole. So N is moles. When we're talking about gas laws, that's what we use as the letter to show. So this one is temperature and pressure are constant. And we're just talking about the moles of the gas and the volume. So if I increase the number of moles of gas, then the volume is going to increase. So this would be just like as simple as pumping air into your bike tire. You're adding moles of gas, which cause your tire to get bigger, expand more. So because it's did I say it was a direct proportion? I don't know if I did. It's a direct proportion again. So as the number of moles of gas increases, the volume increases. So all of the laws, 3 out of 4 of them are direct proportionally. I'm not talking quite right, but the variables are directly proportional. And then only Boyle's laws where they're inversely proportional. So we can actually combine all 4 laws into what we call the combined gas law, because there are times where we might be changing all of these variables. So I'll just kind of talk you through this. So P is pressure, and V is volume, N is moles, and T is temperature, and remember that has to be in Kelvin. So the 1s and the 2s, this, if I say like P1, that means that would be what the original pressure is, and then P2 would be what I change it to. And you're going to do the next, there's a video coming up that shows how to do these calculations. But I wanted to show you that every gas law is in this equation. So this in orange is Boyle's law. This is in the bright pink is Charles' law. And sorry, I'm in the way. P and T is Gay-Lussac's law. And then we've got volume in moles, which is Avogadro's law.